Yeah. I think it should be recording now. Yes. Good. All right. So before we dive right in, we'd like to briefly introduce TNO and VoltaChem for those of you who might not be fully aware of us. TNO is an applied sciences research organization, and we're based in the Netherlands. We were founded in 1932, and since then, we've been working on innovations that can benefit the society, make it healthier, safer, digital, more sustainable. And we do this by developing and applying scientific knowledge in a dynamic, multidisciplinary, and system-oriented way. To do so, we have a team of over 3,800 scientists, consultants, project managers, business developers, working across domains such as energy transition, defense, mobility, ICT, industry, and more, like spread across 25 locations and in 4 countries. And we do this in close collaboration with our strong client base, so of over 2,400 companies, governmental organizations, and knowledge institutes. And VoltaChem is a public-private, internationally oriented shared innovation program within TNO. So it was founded in 2014 by TNO, the Dutch government, and industry, with the aim of accelerating innovation and implementation of industrial electrification options for reducing the carbon dioxide footprint of chemical production. And we do this in very close collaboration with the industry as well by initiating and facilitating collaborative development of technology and associated business models. Our work with, I hear some noise in background. Good. Yeah, I think that's gone now. Thank you. Our work focuses on accelerating the development of new disruptive technologies and taking them from the lab scale to the pilot scale and beyond, thereby bridging the gap between the academia and the industry. Our research to that end is primarily based in 3 program lines. So Power to Hydrogen, which focuses on the electrochemical production of hydrogen and conversion to chemicals. So this includes our shared research programs in next generation PEM technologies and solid oxide technologies. Power to Chemicals, where we work on both high and low temperature electrosynthesis technologies for the conversion of CO2 and bio-based feedstock to chemical intermediates and e-fuels. An example of which is our shared research program in capture integrated CO2 electrolysis. And finally, Power to Integrate, where we focus on value chain integration, technology scouting, economic life cycle and system modeling for the field of industrial electrification. And the initiatives in this include the VoltaChem business community, which is a very unique collaboration agreement with companies from across the value chain, which exchange knowledge and explore interesting opportunities together, as well as shared research programs on value chain and business integration studies. Evaluating the effect of scarce materials is one such topic that the Power to Integrate program would work on, and what my colleague Sara would elaborate a bit more on in her keynote address. So without further ado, please join me in welcoming our keynote speaker for this afternoon, Sara. Over to you, Sara.
Thank you very much, Sarah, for this nice introduction. A short check. Can you see my slides?
Yeah.
Okay. Unfortunately, I cannot see you. So if there are any questions, I cannot see it at this moment. So Sarang, if you would please like to help me with that, then I'll be happy to take some questions. Okay, so I'm very happy and very honored to be the keynote speaker today, and I'm Sara Wieclawska. Short introduction, I'm a consultant at Strategic Business Analysis, which is actually short for trying to get our innovations into a broader context, so into a economic perspective, or into a business case, or into a more environmental perspective, into a more social economic perspective. I'm a chemist. I was educated as a chemist. I'm now 7 years at TNO, and I've been working on the energy transition with a more specific focus since 3 years on critical raw materials and strategic autonomy. And together with my 2 colleagues shown here, I have written 2 papers on critical raw materials in specific combination with electrolysis, and that's what I'm going to talk about today. I'm going to talk 15 to 20 minutes on 3 topics. I'm going to, this presentation is divided into 3 topics. The first is about the scarcity of critical raw materials and how that's a going problem for the energy transition. So actually, what's the urgency? Do we have a problem? How large is it? The second part of the presentation will be about, well, how to mitigate this problem. Are there any solutions and what can we do? And the third one is to put it a bit more in a broader context. It says European context, but it's also a bit on the things we didn't mention before. So first of all, the first paper, it goes more into what is actually the problem and how did this came to be. First of all, we looked, the idea was how many Earths do we need to produce enough green hydrogen for the EU? So we now go from we can produce anything into a more limited stock thinking. We know materials are scarce. We feel sometimes that we cannot get everything we need or the prices fluctuate. And we looked from it to it from 2 different perspectives. One is a hydrogen perspective, which is more in a line of how much hydrogen do we need? What is the hydrogen economy? And what you see here is a development of different scenarios. So this is, you see a figure here of the FCH EU hydrogen roadmap. And in the ambitious scenarios, it states that we need 8,100 petajoules per year of green hydrogen or of hydrogen. We focus on green hydrogen in this presentation. 8,100 petajoules, all right. And to the bottom, you see actually that in the Netherlands, how do you say it in English? The cabinet actually has presented a vision for hydrogen, and it's bound to be very ambitious, and we need the hydrogen economy to scale up. From the other side, we look from a material perspective. So I look more from the material perspective and I say, well, okay, we need wind, we need for energy transition, we need wind farms, we need batteries, we need electrolyzers. They all take materials. So nice that we have these ambitions, but if I have the ambition to build a house, I also know that I need bricks at some point. And in the plans of making this hydrogen economy, the bricks or the materials we need are actually not taken into account that much, or at this moment not. What is also, from this material perspective, a quote that I found is, a low carbon future will be very mineral intensive because clean energy technologies need more materials than fossil fuel based electricity generation technologies. So you can see that to the graph at the bottom right is that actually if you compare the material intensity of the more renewable energy sources, for instance, offshore wind, onshore wind, solar PV and nuclear, that they need more materials to produce 1 megawatt than, for instance, coal or natural gas. So everything comes at a price, and we try to combine these two and say, okay, we want to responsibly have this energy transition. It needs to be done fast. It needs to be done within the boundaries that we have. How much bricks, how much materials do we need? So this was the first question. At this moment, we looked into two of the different electrolysis technologies, AEL, PEM, and we looked a little bit into solid oxide, but we should look into that a little bit more. And we looked into AEL and PEM, and if you look at the bottom, you see the criticality level as stated by the EU of the materials in the electrolysis techniques. And as we focus on AEL and PEM, we looked into the materials platinum, cobalt, nickel, iridium, tantalum, and platinum. So these are the materials we focused on, and we started to calculate how much we needed in total. This ended up concluded in this list, and I will guide you through this table. At the left part, you see the critical materials we were just looking into. Which ones do we need? Solid oxide is still here, but I will tell you about it I will get back to it a little later. So we see at the left side, iridium, tantalum, platinum, etc. And to the top, we see PEM, IEL, solid oxide, and 50-50 PEM, IEL. What you see here is if we would make 8,100 petajoules per year of green hydrogen, and we would do that using only 100% PEM electrolyzers, how much iridium we would need as a percentage of the yearly global production of iridium. So we would need 213% of the global available iridium every year to make this amount of green hydrogen. And this is taking into account that at some point you need to get new electrolyzers and replace them by new ones that take iridium again, and you will recycle, etc. As you can see, for the conclusion was that the largest problem is actually in iridium. Then we have tantalum and we have platinum for AEL. Very interestingly, for solid oxide, the materials that you need are much, much lower. But I will get back to that. And we added a 50-50% scenario as well. Why? Because it's not feasible that you would use only 100% PEM or 100% AEL, because they have their different uses. So they have different characteristics to each of the different types. So 50-50, you obviously divide the problem a little bit amongst the materials, but still it stands that we would need 106% of the iridium that you get out of the ground every year only from electrolyzers for green hydrogen production. And that's a problem because we also need it for other things. Okay, so this is the situation. This is the scale of the problem. But you could also say it's a problem only when you feel it. And at this moment, you can still buy iridium. The price is fluctuating sometimes, but it seems not very urgent. But we have three reasons why it is actually urgent. First of all, the mountain looks small from far away. We really want this hydrogen economy and this energy transition to happen within a certain amount of years. And at this moment, we are still in a scale-up phase. Eventually, the scale-up will look like a hockey stick. So we will scale up in the end probably pretty fast. And by that time, we need to make sure that there is enough material to build all these electrolyzers. At this moment, though, we do not feel the need yet. The iridium is still available on the market. The price is still stable. But there is a possibility that we will only feel the urgency at a very late stage, so at the scale-up stage. Secondly, dependency. Other countries are taking actions, and we are dependent on other countries for these materials, as we will see later. We know this from the COVID vaccine. If you don't make it in-house or you are able to produce it in some way, you're dependent. And thirdly, priorities. So as I said, some of these materials, they have multi applications. They are needed for different types of things. So will we have a struggle there? So are we eventually going into a choice for, do we want to have PVs or windmills? Do we want to have robotics or electrolyzers? That's a question. There might be a clash there. Eventually, we can conclude that the shortage in materials can lead to a delay of our energy transition plans. We do believe that the energy transition will succeed, but it can be such that the bottleneck will be actually materials. It will not be technology. It will not be the fact that we can build large electrolyzers, but it can be the fact that we don't have iridium at the time that we want it. So that's the first part. We have a problem. We have some arguments why it should be on our minds at this moment. So let's look into what we can do to mitigate this problem. This is actually the second part of the paper that we published, and we we've written about the fact that there are several technical solutions to mitigate this scarcity. We focused on technical solutions for the time being, and not on policy solutions, on the other hand, which are still very important. On the technical solutions, we define 3 types of mitigation strategies. To the left, prevention, in the middle, efficiency, and to the right, recycling. What we think when we think about prevention, first of all, reduction, still in Dutch here, but reduction. Reduction of the material as is, making smaller layers, better dispersion of the material. Secondly, substitution by something else. Very important that the substitute is not critical as well. And a mix of electrolyzers. What we mean by the mix of electrolyzers, actually what we just saw, is to use PEM, IL, solid oxide, and maybe any other way of making hydrogen or green hydrogen. It's a diversion strategy, basically. Efficiency is having higher productivity of existing electrolyzers or having a longer lifespan, so you can have a longer time with the same amount of material. And recycling, at this moment, there are 4 different types of recycling strategies. There are chemical processes that can be used to get the critical raw materials out of PEM and AEL electrolyzers. So we looked into these 3 types of strategies, and we can already lift a little bit of the veil here. Reduction has the most potential. The funny thing is that you might have seen that we published something about a reduction strategy. By that time, TNO has published a strategy to reduce the amount of iridium by 200 times in electrolyzers. I'm sure that Reinier or Lennart in the call can tell you more about that. I will get back to it very shortly later. By the time we published this, we did not know that that was happening. So this is very recent. It was not. It actually came to be that this we developed this technique. So getting to these strategies, we defined 3 types. Let's see how much they can reduce the amount of critical raw materials. How we did this, by the way, is to get the electrolysis experts of TNO together and ask them, can you please think of all the different types of strategies and how much it can potentially completely state-of-the-art push it and reduce the amount of materials. Later, we also checked it with electrolyzer producers to check if they agreed on it. Again, through the table, to the left, you see the types of materials and also stated in which type of electrolyzer they are. And at the x-axis, if you will, you see the different types of strategies again. And then let's look into how much they reduce. So as you can see, how to read this table is we see reduction at the top and you see below how much % of the global annual supply is needed to have the same amount of green hydrogen as we saw earlier. So you see that from the 213% we had, you could potentially, in the best possible scenario, reduce to 5% according to what we found. And this is where the spoiler came in. This is before we knew that it was actually apparently possible to reduce this 200 times. So you see that for specific materials, there are different kind of reductions. Substitution, for instance, for iridium, we found it could not reduce. Recycling is quite difficult actually, because you need it beforehand before you can recycle it at the end. So sometimes recycling is a bit difficult there. But we found that the different types of recycling strategies give different types of effect for different kinds of materials, which is logical since they have different kinds of ways that they're in the electrolyzers. Reduction seems to have most potential. We want to give a little bit of a nuance there, as in this is a prediction that we did based on how the materials are in the electrolyzers, but it still needs to be validated, scaled up, and we don't know if this is possible. So we also want to say you have to bet on multiple horses. So you cannot depend on one of these strategies to reduce all the amount of materials that we need eventually for the energy transition or for electrolyzers. This is actually where the TNO research, a bit of an intermezzo, TNO research takes place on electrolyzers. It's the Faraday lab, it's in Petten. And again, just lately, there was a breakthrough and TNO could have 200 times less iridium in the electrolyzer. And we're very proud to have this proven, actually, because again, this is something we work on and we really want to combine material reduction with the green energy transition and make sure it stays on time. Third of all, and the last part of my presentation is about the European context, or the broader context, if you will, European position. To the left, up you see hydrogen. What is being done on hydrogen? Well, there's an FCH roadmap. There are so many things. It's a non-extensive list. There are multiple strategies in the EU. There's an innovation roadmap in the Netherlands. There's a vision by the government. There are multiple subsidies. Basically, people are believing in the hydrogen economy and that it's coming. However, again, the critical raw materials, it is really taken up more space within the Netherlands and within the EU and the public debate the past 2 to 3 years. I know colleagues from mine that have been working on it for 2 decenniums, and they even say it is now finally coming to light that this is very important. If it's the COVID vaccines or the war in Ukraine or the fact that there are price fluctuations, for instance, of lithium because China is making all these batteries and sometimes keeping the lithium to themselves, I don't know. Probably a combination of all. What you can see here are multiple highlights from the past 2 years. At the top, you see a very useful report of the IEA, the role of critical minerals in clean energy transitions, and one of the turning moments into, hey, critical raw materials are seen as a part of the energy transition. So we don't only have an energy transition, we also have a material transition. Or you can solve the energy transition, but you will create a material problem. And that is something we need to look out for. On the EU, there's an EU Science Hub that's actually getting more and more information on there. This plot to the right bottom that you can see that looks like a scatter plot is actually the EU critical raw materials list. So every 2 or 3 years, the EU revises this list. Actually, this year, we were part of a committee that devised this list anew. And you can see which, it's by definition of the EU, which materials are getting more scarce or critical. Unfortunately, the list is only growing. But in the EU, there's a lot of new initiatives and also governmental bodies in several countries. For instance, Belgium, Germany, UK, US are installed to look into the dependency on critical raw materials. So this is something that's now out in the open and being discussed and being investigated, which we're very happy for. Secondly, unfortunately, this is a bit of a downer on the note, hey, we are working on something that's very important and on the reduction of critical raw materials, but that's the environmental impact that we really should not forget. Very small line on this is the fact that raw materials are not for free. So they also take a lot of CO2 costs. It takes a lot of energy to mine. It will be obvious to you that opening a mine or exploiting a mine is something that can damage the environment. And as you see to the bottom of this, the CO2 equivalents from mining critical raw materials can be, for instance, up to 900 kilotons. And it's small on an EU scale if you compare it to everything, but we need to take into account that we are not thinking that, for instance, we should look to it on a whole, from the beginning to the end. So, for instance, if you look at electrical cars, people say, where do the batteries come from? Is it indeed overall better for the environment? We should look into that on this dossier as well. And the last bit that I want to tell you, this was the part on the solid oxide that I promised to get back on, is the fact that we also need to take into account the supply chain. And for instance, for solid oxide, all the materials that are in there have an inherent geopolitical risk. Why? Because you see here critical raw materials. You see in what electrolyzers stack they're used. And you can see that for the solid oxide electrolyzers, the materials come almost exclusively from China. And that's also something that we have to look into. As you can see, for the other materials, there is, for instance, Congo, South Africa, China, Russia. Yeah, well, we have to look into the supply lines, basically. Not all these countries you can rely on for different kinds of reasons. Yes, this is on the fact that materials are used not only for hydrogen production, but also from other things. So we shouldn't have a clash between sectors and have to choose if we use it for energy transition or uses or for something else, but I will not go into that. I think that this is the end of my talk, and I'm very happy to answer some questions.
Thank you so much, Sara. Very insightful. I think we can take 1 or 2 questions and then perhaps move to the next part. So in case you want to have, if you want to ask questions right now. I see a hand, Head.
Yeah, thank you. Thank you for this very interesting talk. So I would be interested to have a copy later on. I don't know if this was discussed today because it was a little bit later. Plus, I have a question. The electrolyzer that you mentioned with the breakthrough, at which TRL level is this right now? Is this already commercially available, or is this still at TRL 6 or something?
First of all, thank you. I will definitely make sure that you get a copy of the 2 papers and or of the slides. And for the question about the TRL level, I will ask Reinier if you can elaborate more on that.
Yeah, sure. Yeah, that's a very good question. And I think the thing is, this is a technology that we have developed, which is patented by TNO. The realism is that this is a lab scale proven thing. So I want to have that disclaimer really in this audience, that it's great news because we are actually very much surprised by the factor that it did the job. But we all know that we need to scale up, and that scaling up brings surprises. So we need to be realistic there. And that's also why we have, by the way, I think a very nice discussion with the people here on the table that are more the experts than actually myself. But this is the disclaimer that is in place because that is to be proven. And it's only proven when it works at the commercial scale.
Thank you very much. It's also good to know that R&D is still important in the field of hydrogen. Thank you.
It is, yeah.
Certainly, yes. I see one more question, which probably we can take right now, and then we move on to the panel discussion. Pablo asks, which are the possibilities for AEM electrolyzers in your opinion, Sara? Would you like to elaborate a bit more on that?
To be honest, I have no. Does it AEL or did you say another type?
He mentioned AEM.
I'm sorry, I'm not. We did not investigate AEM electrolyzers. So maybe you're right. Maybe there's a potential, and we should add that. But at this moment, we did not look into it.
Okay. I see another question, but then I'll keep that for later. Mark, as well, if you could ask that in the later Q&A session. So thanks a lot again, Sara. Very insightful, and I think that really gives us a lot of thought of, food for thought as we move into the next phase of this discussion. Let me see if I can share the screen again. I think I can. It's always a struggle still. Okay. And with that, I'd like to move to the panel discussion. And for that, please join me in welcoming Reinier, who's the principal consultant with TNO-VoltaChem, who act as the moderator for this discussion. So Reinier brings with him about 20 years of experience in the industry and research sector. And prior to joining TNO, he has served as the VP of R&D and the Director of Innovation at DSM. And he's also been a part of the TNO-VoltaChem team since 2019 and works on developing a more strategic vision of the broader electrification and industrial transformation challenge. So welcome, Reinier, and over to you to introduce our panel and guide the discussion.
Okay, thanks, Sarang. Maybe coming back on the question, AEM is anion exchange membrane technology, and that is a new upcoming technology in the area of electrolysis, and it has a different work. It's basically a kind of counterart against the proton exchange membrane, but it requires also R&D and scale up to see where the potential is of this technology. But it was not in our scan that Sara explained. But so just to clarify that for the audience, Happy to chair this session. And maybe it's good to make a tour around our guests here in the room, and maybe I can start with Christian here of Heraeus to reflect on what Sara said from your perspective, basically, and tell a bit what you see in the developments in materials for electrolysis. Please go ahead, Christian.
Thanks, Reinier, and thanks for being here. And I have to just say what Sara was presenting is exactly what we are seeing in the whole market. So I'm from a precious metal house, so we are concentrating or focusing on the PEM technologies, fuel cells and electrolyzers, but the same is true, and you showed it perfectly also for other materials. We have to take care. We want to push, we want to go to volumes, but in the end we have to check how to deal with this topic. And there are three things in our opinion where we have to work on. I think you showed it already nicely. We have to, from beginning on, implement strategies how to source the material, for example, partnerships with countries. We have to, from beginning on, looking on recycling strategies, how to get back the material in the end. But I think Mr. Schumacher just said there's still development inside, and that's also true. We have to deal with our active materials. We have to see something what TNO is doing perfectly, the combination of different components, how they interplay to get down for us the precious metals, but also for the other applications, the critical materials. In the end, this will help, and this will facilitate, and this will enable the green hydrogen industry.
Okay, thank you for your perspective in that. Maybe nice to move on to Sven here. Sven is from Fraunhofer, and I know that Fraunhofer is also doing quite a lot of research in electrolysis. And in particularly also in circularity related to that. So maybe Sven, you can guide us a bit in your world of Fraunhofer and how you are active in this area. Maybe you can unmute, please.
That's always a good idea. Yeah, thank you very much indeed for introduction, and Sara, thank you very much for your presentation. Yeah, so I cannot really speak for the whole Fraunhofer world because we are, I think, up to 80 institutes and 30,000 researchers doing their job. We at IWKS, we do research on solutions for the circular economy. We cooperate with in the field of hydrogen with another Fraunhofer Institute, LBF, with expertise in structural durability and system reliability, and we run a high-performance center, green materials for hydrogen, transferring research results into industrial applications. A little bit advertising here, sorry for that. But when we look at the life cycle of systems and components of hydrogen production, we see three challenges, you can say. The first is the relevant systems and components must be hydrogen ready. So it means if you switch from natural gas systems to hydrogen, you have to check the components reliability of the infrastructure components. So that's a short-term issue which has to be tackled. The second challenge we see, relevant system and components must be made of greener materials or less critical raw materials, which is really the aspects Sara was pointing out quite clearly, which is a more short and midterm issue. And the last point, so we at IWKS come a bit from the recycling perspective, and so the systems and components and materials must be circular. So that means for the first, at the first aspect, design for circularity is important. So when we design today the new systems, we have to see how we can manage or how design these systems that the materials can be better separated in process. And as well. Reuses could be a topic here. Reuse some components, bipolar plates, and so on that we are checking. We need sustainable process in place to reprocess fuel cells. We are just heading a project on recycling of fuel cells. And the third one, Christian pointed it briefly out, it's a collection infrastructure. So recycling begins with collection. If you don't collect or cannot collect, have no access to that, you cannot recycle. And the positive thing is that these elements, especially fuel cells in the automotive sector, there's no second market really in I don't know, around the world often. So we keep these systems in the countries or in Western Europe, where you can implement recycling strategies so that we really have access to the material. It takes time, but we must be prepared. Yeah, thank you. That was my statement on that.
Okay. Yeah, thank you. Can I ask one additional short question, Sven?
Absolutely.
You said about hydrogen ready. That also touches me a bit about, and maybe others can comment on it later, on the safety aspect. So can you say a bit about that, how you look at that? Because I think this is a new technology relatively, and scaling it up to industrial scales will of course require also some real safety dimension in this. Just shortly, if you have something to say on this, then please. Otherwise, I can proceed.
Yeah, what I mean that for example, infrastructural elements like tubes, like valves, but we have and now they get in touch with hydrogen, maybe deep cold hydrogen, and they need specific materials and specific tests routines, whether these are really, to say it ready, or let's see, are capable to manage these kind of new mixture of gas, containing hydrogen. Yeah,
thanks. That gives an indication that it is a point of attention. Thanks for that, Sven. A completely different angle to this, I think, can Florian bring, I think, here in the room, because it's more about standardization, Florian. So please enlighten us on standardization in hydrogen production.
Yeah, I'm from the VDE. We're a technology organization, and we focus on standards and also norms. And I think standardization is a very powerful tool because it makes a bridge between research, industry, and also recyclers, and bring together the different requirements and specifications of all stakeholders along the whole value chain, also the different viewpoints and knowledges. And I think that's very important also in the field of electrolyzers to look at the whole life cycles and bring the people together to know what happens in the end with the electrolyzers, and so that the, for example, recyclers are prepared and also bring their opinions in, and maybe so with this to connect to Sven's viewpoints to bring the circularity in the market. Maybe also it's possible to bring in some iridium loadings, or also new research knowledge about alternatives in critical raw materials. I think also it's crucial to make this in a very early stage, to bring the manufacturers and all together to make guidelines for all the stakeholders, also for the manufacturers, that they know what the market are needed in this field and what the market expected here, and the recyclers also. And I think that's a big topic. Also, seals of approval can help here to make like recycling readiness seal of approval or something like this. Yeah.
Okay, thank you. Do you also see some opportunities because you say standardization that also maybe components in the industry can be kind of standardized and exchanged, etc. Because I think the challenge that we are facing is it's basically not a matter of do we have to do it? It's more like how the hell can we accelerate? So in what sense can standardization help us to accelerate this innovation and basically make it commercial available? Because I think that's the huge challenge. If we look to Fit for 55 for Europe, already that is, I think, a huge challenge. And to put the pressure on, I think it's good, because then we all get very creative. So what can standardization do to accelerate all of this?
To accelerate, I think from the material challenges, I think there are a lot of research programs, for example, for deconstructions, also in the kind of ceilings, to bring this together for this. And I think also if we have some standards here, this can help at the end there.
Yeah, sure. Thanks for that comment. I think now I like a perspective actually a bit on the manufacturing side. Like I said, if we want to accelerate, then it's all about, I think, also going from a kind of manual manufacturing towards automated manufacturing, and how can we speed up there? And I think that's one of the elements that also my colleague Oscar can tell a bit about. So Oscar, welcome, and share a bit your view in this matter from your perspective from the Holst Centre.
Yeah, thank you very much, Reinier, and thank you, Sara, for putting together this very nice webinar. Yeah, actually commenting on that, there was a point that triggers me in the presentation from Sara, which was the final table where she comment on the strategy for like to tackle the challenges, and she was commenting in regards to reduction and efficiency. But I think an important point here will be the synergy between them. And actually, I saw, as a matter of fact, I saw actually in one of the comments in the chat somebody commenting about mixed oxide DSAs. Basically, we need to actually think in the manufacturing, not in a single matrix view, but basically thinking in the synergies. And in that regard, the high-tech manufacturing enters, and not only thinking in the high-tech manufacturing, thinking in the terms of top inch technology, but basically looking in previous technologies, because an important point that we need to take into account is high throughput, because we need to produce catalysts, as much catalysts or as much electrodes for electrolyzers as fast as possible. So basically, we would like to have something that is a mature technology. So when I say next generation or high-tech manufacturing, I'm basically thinking of taking a set of technologies and advancing one step further. To put an example, electrodeposition or electroplating. That's a very old-standing manufacturing technique. But what we can do to actually do it to basically deposit in specific regions, because an important point that we need to take into account is utilization. Since we're basically talking of critical materials, we need to optimize the utilization of these materials. So we need to place with the manufacturing, so to basically tune and fine-tune engineer the way we manufacture. I mean, and we actually need to do that being as technology agnostic as possible, thinking what is the problem we basically have, and then look into the whole portfolios of technique, new and old, and then basically start developing. That's basically that is the view that, for instance, a breakthrough that was mentioned about the 200 times less iridium. That for instance is a technology that is based in spatial ALD that was optimized and basically you can put iridium in a very specific region of your electrode to optimize the utilization.
Okay, that's a nice perspective. So you're also saying, if it's clear I'm not the expert here, so that's nice to be not the expert. So if you think about the materials efficiency, you mentioned, are there also big differences between the deposition technologies and the material efficiency, so that you have less losses or can reuse, or is there anything you can say or share about that?
Yes, and actually that connects a tiny bit with another point that is related to the circularity, because you basically want to make the material that is as efficient as possible using the least possible, but you also want to minimize the spillage. So basically you want to make the manufacturing, so basically being sure that all the critical materials you put in there are basically utilized, and what is not utilized is reused.
Mm-hmm. Sure, yeah. Okay, thanks for that. Maybe to the whole, let's say, panel that we have here, I would like to make a tour, like, if you look forward, and you look from your perspective to this theme of scaling up, accelerating, be material efficient or effective, what would be your dream, basically, to get this accelerated? So what should happen in your view, and what would be the biggest thing that you think needs to happen from your perspective to really accelerate and come to the incredible amounts that Sara showed of the amount of basically the scale that we need this technology? So let's make the tour again. So maybe Christian, you can maybe comment from your side, from your material perspective. So please.
Yes, first of all, I have to apologize. It could be a bit loud in my background because here I am on the fair at the Hydrogen Week. So if there's something beeping, I'm not moving backward. That's something here in my back. So no, but that's a good question. And to be honest, during you raised this question, I was afraid that I'm the first one to answer it. But no, it's right. It's something I think everybody said already. We know what we do. We are aware what's coming. And I would answer it like this: we don't have to be afraid of it, because this time that's really something which is also helping. So volumes are nothing we have to be afraid of. However, now comes the real answer on your question. We know where we have all these small tweaking points on the material, looking for substitution as a best way for iridium, if you talk about iridium. But we have a way to this point. We don't have to make it actually tomorrow. Now it could be in 1 year, in 2 years, 3 years. We're growing with the ramp up of hydrogen economy. However, coming back, we have to be aware that we have to do it, and that's maybe for me the main answer, since we are not only working on the catalyst material itself, but having also a deeper look in interaction. You cannot do it alone. And also PEM cannot do it alone, AL cannot do it alone, even electrolyzers cannot do it alone. So we have to have really work together. We have the expertise on every field. Oscar, you said perfectly, and I was also happy to see the publication of this nice note with the 200 times better, because I knew in which direction you're going. There are many tricks we can still do to get to the point, and we have to work together. That's I think the main point. Because last thing, one component alone is not the answer. You have to know what the other is doing. So that's the main point.
Yeah, that's why I'm so happy that we are together in this type of webinars, that we can share these thoughts. So thanks for that, Christian. And I see Sara asking for a comment, I think, or for.
Yes,
Go ahead.
I'm a bit triggered by Christian saying we cannot do it alone. So no technique separately can do it alone. No party can do it alone. And this makes me think I'm getting quite interested in what you would expect from policy as a support. And I can imagine two kinds of policy, maybe there are more, but two kinds, for instance, the policy that supports investigation into technical mitigation strategies, so into subsidies for technique, and policies that would actually safeguard the amount of materials that are available for instance, electrolyzers to begin with. And I'm very curious what you think and what the role of policy should be the coming 10 years, for instance.
I don't know if you directly ask a question to me, but I will answer first.
Yes.
Go ahead.
Yeah, so there was a big discussion here in Brussels during this Hydrogen Week on this topic, and everybody had to apologize, but we have to look to the US. They are not punishing, they are not pushing, they're giving incentives or mitigating risk. So everything of those measures helps to accelerate innovation, to accelerate taking risks, making business cases, and that's exactly what we have to do. We have to in principle, getting incentives to those who trying to make it possible. And that's the way to do it. So if we really want to accelerate new developments, we cannot give funding, and I'm now a bit offensive, to be honest, but we cannot give funding to a new project where an old material is inside. We have to give funding to things which are the next generation, where we go to this ramp up, where we can manage this ramp up. And I think that's something policy wants to make it now possible that we have a hydrogen economy, and that's great. That's really great. But we have to think about the next or the over next generation. And that's always new material.
That's nice. You're triggering people here, Christian. So I see Oscar really willing to comment. Go ahead.
Actually, Christian triggers me when exactly that point, because, for instance, when you look into like reducing, sometimes we basically think of like, basically looking into the next generation, but sometimes we forget look into the past, that basically there is a huge battery of materials and a huge database of materials. But basically, when it comes to applying for funding, I mean, or getting funded, commenting in the point of Sara or policies, then basically, if you basically start digging from the past, then you look less innovative, and then basically become less attractive at the moment of applying for fundings.
Yeah, maybe I like that what you say, Oscar. I sometimes have a bit the time that we are in Europe, and I think it's generally because I'm also in the SUSCAM board in Brussels, and this is interesting thing. Sometimes I have the idea that in Europe we have a tendency or a culture to innovate in all kinds of new stuff, but forget to implement. So and sometimes I think, what technologies do we already have that are kind of proven, and let's first scale those up and make it happen, and then indeed also, of course, improve. But I'm not saying we shouldn't innovate. Sure, we should for sure innovate, because Sara showed that we need to, otherwise we run into issues. So that's not my plea, but my plea, sometimes I feel like other parts of the world are more, let me challenge us here a bit, are more on the implementation rather than on understanding it all and just go. And I think that's finding that right balance probably then you can be very, very successful. But that's a bit my weird mind maybe, but for now.
Reinier, that's funny that you say this, because it makes me think a bit about these discussions, these lock-in fears that we have. Well, why would we invest in this? Because we can invent probably maybe something that's much better. And in the meantime, life happens when you're making plans.
Exactly. And then you get the kind of analysis paralysis situation, and that's not helping. And I think if I see the clock ticking for all of us, and I see the fantastic but very challenging European targets, then yeah, I would say go, go, go. We need to to really learn by doing as well. And indeed, I think that's also clear here. We are all in this boat, so it's all about help each other to accelerate. But let me stop the talking. I want to have still a kind of reactions of Sven and if you allow me, Oscar, for one moment, of Sven first, and maybe Florian as well on this.
Yeah, I mean, we're all smart researchers at TNO, Fraunhofer, and others. So I think the technology development, I think this is easy. Okay, it's not really always easy, but I think we can manage together with companies like Heraeus and so on. What we need is, of course, a political framework, which is a bit accelerating. Could be better, because in Germany it's the focus is more, for example, for the traffic, for more electric cars, even though fuel cells is as well electric car, but you know what I mean. So with accumulators. But in the past, I fear that a little bit negative acceptance of the society. But in the meantime, it's changing. So the past people say, "Oh, fuel cell." So in German, it's a Brennstoffzelle. So there is something that's burning in this one. They fear. Yeah. I said, no, there's nothing burning. It's called
stop burning.
So, but no. But hydrogen, my good, it's exploding. The Hindenburg and so on. And I said, no, it's a completely different story. So we can manage. Yeah, and people change. So maybe. One short funny thing. So I have a neighbor, he is banker, and he told me, this is so expensive. There's no ROE, so maybe in 20, 30 years, that's my piece of cake. I don't invest in solar energy, PV. It's not. And another neighbor, he's a chef, he's a cook, but he's open to other things. Yeah, I would purchase. Today a fuel cell car, and it must be great. I don't like the batteries and so on. So there's a discussion coming up, I want to say, and this will be helping us to implement, and and people see it's important. We have no chance. There's no way back to natural gas. So
I would say particularly now we have learned that. So in Europe. Yeah. So yeah.
Bad example.
Thanks for that. Okay. Yeah. Thanks for that, Sven. Florian, what's your view on this? And I think then we have to round it off a bit. So go ahead.
Yeah. I think so. From the perspectives of the standardization, so in the end we have to put everybody together on the table, and everything also on the table, and yeah. Try so together to tackle this problem in the end.
Okay, super. Yeah. Well, maybe to close it off a bit. I think it's a separate discussion even on. I mean, that we need to basically have a hockey stick in this technology is obvious. Whatever you can find about applications developing, yes or no, or. Because that's the other discussion, of course, of demand. And I think there you can be very critical if you look to the applications of hydrogen. But in all cases, we need a hell of a lot of it. And so that's not a discussion. It's a matter of bringing this forward, match it with the raw materials availability and supply demand in that area. I think that was the big thing of today, where Sara really showed where it can or where it will, I think, also start to become could become nasty, or could maybe slow down what we want to achieve. So I think all in all, we have a nice vision here from all of us to this important topic. So I want to thank you all for that from the panel, but I would like to stay the panel in, of course, because there might be Q&A from the audience, which is interesting, and where we want to give the floor now to. So I give back to Sarang to basically manage the Q&A.
Thank you so much, Reinier, and to all the panelists. Extremely interesting discussion. And I also think it's very interesting that a lot of it links back to what Sara was saying as well, that we need a combination of techniques and how urgent the problem really is. And that is very clear from all of your talks as well. So thanks, all of you.
Sarang, let me take one thing. We don't have a problem, and I don't like the to make it smaller. It's a challenge. It's not a problem because we know what we're doing. I have to say this. Sorry.
Very nice comment, though. Completely agree with that. I would like to move it on for the Q&A, indeed. And this is the time when we'd like input from you, the audience, for all our speakers so far. So if you have any questions, please drop them in the Q&A box, ideally, so that it's easier to track, or raise your hand if you want to comment or speak.
Yeah, Sarang, there are already a few questions in the Q&A, so maybe you can guide them to the right persons. If yeah.
Indeed. There was, while the panel discussion was going on, there was a lot that was popping up. Perhaps we go to Mark first, and I'll come back to that. Mark.
Hello. Hi, thank you for taking my question. And thank you for a very interesting talk, Sara, and a very good panel discussion. I work for Johnson Matthey. I'm a research scientist, and I've been doing some modeling, perhaps a little bit similar to what you've been doing, Sara, but I've been focusing on iridium. And my comment is just about recycling iridium. We know that iridium has a fairly high recyclability in its current applications. And I think, when the scarcity of iridium, if it really hits in the future, there'll be a big incentive to recycle it from PEM electrolyzers. And in my own modeling, I found that it could make the difference, really, or it could be a big contributor towards the sector not being limited by iridium supply. And just to link back to the policy question that was in the Q&A, my input would be that I think if policy was able to incentivize recycling and a recycling closed loop infrastructure before there was an actual real financial business case for that, so that when that first sort of glut of iridium comes out of your PEM electrolyzer marketplace, you've got the system, you've got the infrastructure ready to go. That would be a really important thing to policy to drive, I think, because if you start building the plants for recycling when the material's coming out and you need it straight away, that's not going to work very well.
Thanks. The first question that I have is what assumptions you made in terms of how the recyclability, what it would be, but also because if you have a hockey stick of implementation that you will need, because now we looked into linear implementation. So what if you divide 8,100 petajoule over all the years we have now until 2030, 2050, which is not the case, obviously. And I can imagine that if you have, for instance, if it's 2029 and you're ramping up production really quickly, you need a lot of iridium in that particular year. And then you will not be able to recycle it for the lifetime of the electrolyzer, which will be 7 or 8 years or whatever you want to take. So I would be happy to discuss it more and see what your takes are on it, because maybe we can refine this study, or maybe we can help with another study that make, there's how you say, it's building up knowledge basically and making it more better. Yeah, thank you.
Yeah, absolutely. So on the sharing knowledge bit of it, we will be publishing a paper on this in the next few months. So it will come out on the percentage of the yield of recycling that we've assumed. I do the whole scale. I do a sensitivity study, so you can pick whatever you think it will be. Quite hard to say. I think it could be upwards of 80%, but it also all depends on not just the technical recyclability, but the metal actually needs to get to a recycling plant and not end up in landfill somewhere or something similar. Yeah, and on the second point, just very quickly, so I'm aware I'm taking up time. The advantage of a hockey stick model, I think, yes. So if you can grow your electrolyzer capacity gradually at first, and let iridium accumulate in the system by recycling it, that would really enable you to then grow it really quickly up to 2050, say, is my conclusion. Otherwise, if you don't do that and you try and grow it linearly or somewhere close to linearly, you get a massive peak in iridium demand early on, as you said, because recycling hasn't kicked in yet. Yeah, thank you.
Great, thank you. I would like to go back to a couple of questions in the chat before we go on to Koma. I'm not sure how to pronounce your name. I really apologize for that.
Yeah, no, that was not bad. I'm sorry, my camera doesn't work. Jerome, I work for NET. It's a new energy technology fund. I'll be very interesting to hear a little bit the latest status on those recycling processes for those different materials. Because of course, if this needs to be a key part and a key enabler of the deployment of these technology, I have to admit that I haven't found too much on it, and I'm wondering, as per, let's say, the solar industry, to take a metaphor, you know, this has taken a very long time to be set, to be implemented, to be deployed in even on the legislation part. And so I'll be keen to see a little bit your view on these processes and the actual industries ready today to deploy such a processes, and making sure that they are maybe even sort of coupled with the production factory sectors, or how could we, you know, ensure a well gathered, because as you, sorry, I forgot your name just before the comment of mine. It was really interesting to hear that, you know, there is two ways to face this critical needs, and one of them is to, you know, make sure that we take this on straight on, which will accumulate in the system and create an ecosystem of recycling, and then deploy it at large scale and allow us to deploy correctly the hydrogen sort of alley. So I'll be keen, yeah, to hear a bit more.
Sven, do you want to say something, or should I start?
Please start.
Okay, sorry. Yeah, let's give me a short answer it first. So we have to differentiate between process and process. So the process of refining from waste streams precious metals is an established one. So in our house, for example, we processed last year 2 tons of iridium via the recycling process. So already a fairly high amount of material. So processes for precious metals, getting back precious metals, are completely established. Of course, optimization on every step to get the last bit out of it is always necessary. However, even this process is one question mark inside. Do we want to get additional value out of the waste stream membranes? I don't want to tackle it now. I tackled this week a lot discussion with polymer producers, manufacturers. I think in 2 years we have a new panel on it. But nevertheless, coming back to the second process, which is the one I think also Sven can say something, how to get back the material, how to get back, dismantle it, how to get really the part of those things to us, to those who are recycling, refining. That's the main question. And last thing, electrolyzers are not moving. That's a good thing already compared to a fuel cell. However, especially if you're talking about these different technologies of electrolyzers, then the question or those processes has to be established.
Christian, I now you trigger me, sorry for that, but do you also think about ownership business models, that you own the material?
If I'm saying no, I'm lying. If I'm saying yes, I'm saying too much. No, it's something. Yes, of course, we're talking about a lot of capex. So in the end, it's a question: who's the owner? Who's the owner? Those who are making the stack, the one who's using it in the end to producing hydrogen. Most probably we are not the owner anymore. That's maybe out of the thing. But yes, that's not settled, and there's a lot to come. And sorry that I'm talking so much, but that's a problem in such a ramp up. We have to think now, not when we need it. That's the main point here. Now I'm stopping.
Yeah, thank you, Christian, for the start. So sure, processes are already implemented, but always can be improved. You said that with the membrane. So when we look at the fuel cell as a whole, we have the catalyst, of course. We have the membrane, which is a quite interesting material for. Might be interesting for recycling because it's a high value. It's Naphthalene. Yeah, you pay a lot of money per kilogram. You have other parts like the bipolar plates. Might be an issue of reuse because there is a high value added in manufacturing them. And so these processes will develop further once you get back the material. The comparison to the PV, what was stated before, because there was a kind of legislation, and then it was clear that they had to be collected. There's one big difference. The big difference is that there is an intrinsic value in the fuel cells, which is much higher than, for example, in case of photovoltaics. So today, photovoltaics, I know that because in parallel I work for the recycling industry, for electronic recycling, and it's very difficult to get rid of or find a good process because these companies are waiting for the materials, but PV panels are on the roof, and once they get exchanged, they still produce energy. So there's a market for that. So the market is more for these products for the reuse, let's say, for the fuel cells if they are done due to several reasons, dirt or corrosion and so on. They will find a way for recycling. Nobody will dump it due to the platinum value, and we can much more improve the process once, of course. The content of platinum should be reduced in the future, so that the company is working on reduction. So we have, as in the recycling phase, more to concentrate to get a better added value from that, and we see that in the platinum, but we see it as well in other components.
Thank you. I see that there are a bunch of questions in the chat about materials, which Matti also helped to answer. So thank you, Matti, and to the people who asked the questions as well. And there were a few discussions about the environmental impacts as well, to which Sara responded, as well as with scaling up. So I think we have covered quite a lot of the questions that are already in the chat. If other people would like to comment, they could also put them in the chat. Or perhaps raise their hands right now. I think we were a bit too effective in driving home the point. Okay, Aaron.
Yes, hello. I'm from DAFTA MP. I have a question about replacing the critical raw materials. Is it a knowledge problem that we have that we cannot replace iridium and platinum? Or is it proven that there is no other catalyst available that could do the job in the harsh environments of, for instance, a PM electrolyzer?
I think I can take this. Actually, the challenge does not lie in either of them. I mean, the material is known. It's actually, I mean, one of the material. That's what I basically say of looking into the past. I mean, the material is known, and I can actually name it. It's ruthenium, even though it's the challenge comes into like into manufacturing and basically again into like how to basically get do some extra research into, for instance, do conformal, do tiny coatings, etc. That basically points again into like getting founded to actually do that.
And what about composite materials? For instance, I know Stanford has a publication about the platinum titanium alloy that has a higher catalytic activity and a similar stability compared to platinum. So if we start mixing, basically titanium is relatively cheap with platinum, we can reduce the amount of critical raw material needed. Is there research at TNO about something similar?
Currently not, but basically I mean, because basically when you talk about platinum, then you start talking about the cathode of the electrolyzer, and over there is a very big space to actually do innovation or modification, because you don't need to deal with corrosion. Actually, you can even go into non-PGM materials. Without losing too much of, I mean, you can go to molybdenum or tungsten without losing too much of activity.
I see. And what about iridium? Is there an alloying process that is known or proven?
Well, the one I mentioned, for instance, the mixed ruthenium iridium, or like I saw it as well in the chat. That's not aiming too much towards activity, but for stability. But iridium tantalum, all those are stuff that basically are actually on the table.
Thank you very much.
Let me add one small.
Sorry, if I may just comment on that briefly. Be aware that ruthenium is a chlorine producing element, while iridium is an oxygen producing element. So it is really a different thing. Although it's a noble metal, the wear rate will be a lot higher for ruthenium. So yes, there is more ruthenium, but you will need a lot more for this application. So it's not the best route.
And let me add maybe one thing. Nice to see you, Aaron, by the way. That's also part which is away from which new material to use. There is always, and we talk about a very conservative business, you have to always guarantee that this electrolyzer is running for the next 20 years. So to really implement, and that's what I mentioned before with this project, we should go to the next generation, because it's the only chance to test something new, because the big OEMs will not use it by instantaneously. They want to have a proof that this is running for the next 20 years. That's I think the biggest hurdle at this moment.
I would like to actually comment on the point that Matti made very briefly. That I mean, I do not actually agree that the part of generating chlorine would be a problem of putting considering ruthenium, because we actually, I mean, something that is intrinsic into the PEM electrolyzers, for instance, is working in the mineralized water, because if you have chlorine will not be alone in there. If you have then you will have cations, and then you will kill the membrane anyway.
So now we are talking. We got a real discussion. I like it. Anymore, I see also some other people want to say something. Later. So yeah,
exactly. Yeah.
All right. Thanks a lot. I really like it as well. Sylvan, I see you were second.
Yes. Yeah, I've not really a question, but a remark on the answers Sara gave on my questions. And it's true that there's a really environmental impact due to the extraction of minerals and things like that we need for electrolyzers. I think we should address it right now, because otherwise the business runs the risk, like other renewable solutions like bioenergy, and we kill the baby in its infancy. So I think it's very important to address also these other environmental aspects Sara mentioned in this in answering my questions. That's my remark on this.
Yes, I agree with you. The only thing is that we decided to look into only, like, is it a problem for electrolyzers at this moment? Mm-hmm. But these kind of questions then start popping up, like, aren't we digging one or fixing one hole and digging another?
Yes.
I don't know, because I don't want to put you in the spot, but I've seen Mara Haug, and she's I think a specialist on environmental impact of materials. I don't know if she's still here. But we do have colleagues that work especially on environmental impact, okay, which is maybe their next task. Hello, okay. Mara. Do you know more details about the impact of the mining.
I must say I have not looked in those materials myself, but generally, yeah, mining comes with substances that you need to get the ores out and to solve stuff that's generally not too healthy.
Okay.
So, yeah, of course, it makes sense to look into that early on, like the social aspects as well, of course, which is not my expertise, but kind of belongs to the life cycle thinking part of this.
Okay.
And that was the word I was looking for, life cycle
analysis.
thinking,
Okay, thank you.
But hopefully with a lot of recycling that we've heard today, you can at least recycle it for some cycles before leaching it again into the environment.
Yeah, and don't forget that there are innovative startups working on mining without digging a mine. Eh? So there are also technologies upcoming here which are very promising.
Okay, let's help them then.
Thanks, Sylvain, for bringing this additional dimension to the table as well. I apologize, Anya, but we are really running out of time at the moment. So if you could send me the question at a later stage, I'll ensure that it gets redirected to the person that it's intended for. And that goes for everyone attending the conference as well. I'd like to round up the meeting looking at the time as well. So let's see if the screen works again. I think it does. So thanks a lot, everyone. It was a very nice discussion. And if you're interested, before you go, if you're interested in working on challenges like this, we do invite you to join us at TNO-VoltaChem as well. One example of which could be the shared research program on next generation PEM technologies, from which you saw the breakthrough just a little while back as well. If you're interested in working on that, please contact Lennart van den Berg. And if this kind of discussion or this kind of topics interest you, please consider joining the Power to Integrate program of VoltaChem, where we work on broader strategic problems such as this, including economic, life cycle, and so on problems. Or if the format of the talk also interested you, please consider joining the business community, where we do this every month. And we host more such discussions on various topics around the topic of industrial electrification. And if you're interested in that, please contact Iveta. With that, we come to the end of the webinar. So thank you so much, everyone, for attending.